Hi, welcome to Features of the Gaussian, or Normal Distribution, Part 1, Mean and Standard Deviation. So, a function of the form here denoted as f of x given mu and sigma is called a Gaussian, or normal distribution. This is the first of two videos where we talk about features of the Gaussian distribution. In this video, we're going to discuss general features of the Gaussian distribution, such as its shape, mean, and standard deviation. In Part 2, we'll talk about some features of the Gaussian distribution that come up frequently in statistics. The Gaussian distribution, also called the normal distribution, is important in a wide range of contexts. For some examples, you can check out the video Why the Gaussian Distribution, or Normal Distribution, is Important, available on this channel. For mathematical details on how the Gaussian distribution is a limit of the binomial and Poisson distributions and of a random walk, you can check out the other videos in the Gaussian Statistics playlist. Let's start by looking at the form of the Gaussian distribution. It's a function of x, and it takes two parameters, mu and sigma. First, let's plot a few Gaussians with different values of mu and sigma. Let's start with the easiest case, where mu is equal to 0 and sigma is equal to 1. We can see that f of x given mu equals 0 and sigma equals 1 is a symmetric bell-shaped function centered at 0. Now let's see what happens when we change mu. So here we've drawn a Gaussian for the case mu equals 1, sigma equals 1 in the green curve. Note that the curve shifts to the right by 1 unit. And now let's look at the case where mu equals minus 1 and sigma equals 1. So here that's shown in the blue curve. The curve shifts to the left, and now the peak is at x equals minus 1. We see that mu is the location of the peak. This is true generally. So let's see how this arises from the formula for f of x given mu and sigma. The exponential contains minus x minus mu squared over 2 sigma squared, which is always less than or equal to 0 and decreases as x moves away from mu. So the function is maximized for x equals mu, because then we have e to the 0 power, which equals 1. Also, the function is symmetric around x equals mu. The value will be the same for x equals mu plus delta as it is for x equals mu minus delta for any delta. Okay, so now let's see what happens when we change sigma. Here we'll start again with the case mu equals 0, sigma equals 1. And note that we've changed the scale compared to our previous plots. Okay, now let's look at the case mu equals 0, sigma equals 0.5, shown here in the purple curve. So two things have happened. First, the width of the distribution has been cut in half, and second, the peak is now twice as tall as it was before. Next, let's look at the case mu equals 0, sigma equals 2, shown here in the light blue curve. We see here that the curve is twice as wide and half as tall as the mu equals 0, sigma equals 1 case. Let's take a look at the formula for f of x given mu and sigma and see why this is the case. First, let's look at the width of this distribution. Okay, so we have our formula for f of x given mu and sigma. Again, let's look at that exponent, minus x minus mu squared over 2 sigma squared. When the absolute value of x minus mu equals sigma, the function will have dropped off from its maximum value by a factor of e to the minus 1/2, which is about 0.61. So for larger sigma, the absolute value of x minus mu must be larger for the function to drop off by the same factor, and this produces a wider peak. Okay, next let's look at the height. At the same time, the height of our function at x equals mu is 1 over the square root of 2 pi sigma squared, which is about 0.4 over sigma. So the width of the distribution scales with sigma, and the height scales as 1 over sigma. This dependence of the height and width of the distribution on sigma is very convenient. In particular, if the width of the peak scales with sigma and the height scales as 1 over sigma, the area under the curve will always be the same, regardless of the value of sigma. In fact, the factor of 1 over the square root of 2 pi sigma squared in f of x given mu and sigma is chosen so that this area is always 1. Let's see why this is useful. The Gaussian distribution arises frequently when talking about probability distributions. Let's look at an example of flipping a fair coin which, on average, comes up heads half the time and tails half the time. Let's say that we flip this coin 100 times. Of those 100 flips, how many come up heads? Now, on average, it comes up heads 50 times. But that doesn't mean it comes up heads exactly 50 times when we perform this exercise. The probability that the coin comes up heads exactly m times is given by the binomial distribution. For more details, you might want to check out the videos in the binomial statistics playlist. In the video, The Binomial Distribution for Large N, we saw that if the number of coin flips n is large, the binomial distribution is well approximated by a Gaussian distribution. For n equals 100 coin flips, the Gaussian approximation to the binomial distribution is pretty good, as we'll see in a moment. Here we plot the probability for the coin to come up heads m times out of 100 flips. The exact binomial result is shown in blue, and the Gaussian approximation is shown by the red curve. For example, the probability for the coin to come up heads 50 times is about 0.08, or 8%. The probability for it to come up heads 45 times is about 0.05, or 5%. If we sum the probabilities for all the possible values of m, the sum must equal 1, or 100%. Each blue bin in the plot has a width of 1, so the area of each blue bin is equal to its height. So summing the probabilities is equivalent to summing the areas of the bins. So this means that the total blue area equals 1. The factor of 1 over the square root of 2 pi sigma squared in the definition of the Gaussian is chosen so that the area under the Gaussian curve, shown here in red, is also 1. More generally, we don't have to compare a Gaussian to a binomial distribution to use it as a probability distribution. Let's say the position of an object is a random variable which is described by a Gaussian. Let's say we measure the position of the object. The object can be found at any point between x equals minus infinity and x equals infinity. But it is very likely to be found near the middle of the distribution and not very likely to be found in the tails. So for example, in the Gaussian plotted here, it would be very likely for the object to be found near x equals 0, but not very likely for it to be found near, say, x equals 3 or 4 or 5. So here we're using the curve as a probability density function. The probability for the object to be found between x1 and x2 is given by the area under the curve between x1 and x2. So here, the shaded area between x equals 1 and x equals 2 gives the probability for the object to show up somewhere in the region between x equals 1 and x equals 2. Now, as the object must show up somewhere, the probability for it to show up somewhere between x equals minus infinity and x equals infinity must be 1. So the area under the curve, if extended from x equals minus infinity to x equals infinity, must be equal to 1. Next, let's briefly discuss the mean of the Gaussian distribution. Take the above example of an object whose position is a random variable described by a Gaussian distribution. If we did this experiment many times, what would be the average position of the object, here denoted as x in brackets? We won't calculate this, but just argue from the point of symmetry. As f of x given mu and sigma is symmetric about the point x equals mu, the average value of x must be mu. So the mean of x is equal to mu. We could also ask what the standard deviation is of the object's position. We won't show this here, but we'll argue using results from other videos that the standard deviation of x is equal to sigma. First, let's consider the binomial distribution again. As seen above, for a large number of coin flips, it approaches a Gaussian distribution. Specifically, the binomial distribution approaches the distribution shown here, which is a Gaussian with sigma set equal to the square root of ph, pt, n, where ph, pt, and n are parameters in the binomial distribution. We also showed in mean and standard deviation of the binomial distribution that the square root of ph, pt, n was the standard deviation of the binomial distribution. So we can see in this case that the standard deviation of the Gaussian distribution must be sigma. We can make a similar argument using the Poisson distribution. We showed in the video the Gaussian distribution, or normal distribution, from the Poisson, that the Poisson distribution, in the case of large lambda, where lambda is the mean of the distribution, approaches a Gaussian distribution with sigma equal to the square root of lambda. Also, we saw in mean and standard deviation of the Poisson distribution that the standard deviation of the Poisson distribution was the square root of lambda. This will also hold in the large lambda case where the Poisson approaches a Gaussian distribution, so the standard deviation of the Gaussian distribution must be sigma. Okay, let's summarize. Here we've seen some basic features of the Gaussian or normal distribution. We've looked at the general shape of the distribution and seen that mu defines its mean value and sigma is its standard deviation. In part 2, we'll focus on the probability for a Gaussian distributed random variable to take a value in specific ranges around its mean.